Good morning, friends. How are you? My name is Ashutosh Garg. I work for Furnace Improvements. Welcome to our webinar on efficiency improvement dampers. Prior to 2020, most of us did not know anything about webinars. We were always talking of face-to-face meetings, trainings, and then COVID came and everything stopped. And I remember sitting in my office and doing a Google search on webinars and trying to find out how to conduct a webinar because I started getting a lot of invitations. So we started learning about. And it turns out it was a very easy process. And it took me about 2 or 3 months to learn and get the presentation ready and do my first webinar. And since then, we haven't stopped. We have found it to be a very effective medium of communicating with all our customers, clients, you know. So we might have done at least about 20 to 25 webinars on different topics, mostly related to fire heaters. Uh, and today, this is our first webinar which we have specially conducting for our Indian clients. So I'm in US and it's 10:30 in the night. Uh, most of the webinars what we have conducted in the daytime for American customers, or Indian people from India and other places have joined us in their evening. So this was a new experiment, and I'm very happy that more than 50 people have signed up for this webinar. So let's begin. Today we are going to be talking about a very small component of a fired heater, stack damper, and how our design or patented design of efficiency improvement damper can help you save money and reduce emissions. So that's what we will be talking about. Uh, Most of you, I hope you know me by now if you have attended our previous webinars. I passed out from IIT Kanpur in 1974, chemical engineering, and I've been very fortunate. I have worked for almost 50 years now. 2 months ago, we celebrated our 50th anniversary of working on combustion fired heaters. And for the past 28 years, I've been working in my company called Furnace Improvements. So, and I love sharing knowledge because the more I share, the more I learn. So that has been my philosophy. Uh, Before we start the webinar, we have to talk little bit about Furnace Improvements because they are the ones who are sponsoring this webinar. So Furnace Improvements was started in 1996 in Sugar Land, Texas, USA. We completed 28 years in March 2024. Our engineering office, which we opened in 2005 in Noida, is the main office. And our approach has been a contrarian approach. We have been challenging conventional wisdom. Fired heater designs are about 100 years old, 120 years old. A lot of things have changed, and we have challenged conventional wisdom And as a result of that, we have 3 patents. We have a patent on split flow technology. We have about 12 installations. We have patent on inclined firing. You can find webinars on split flow and inclined firing on YouTube. And today we'll be talking about our latest patent, efficiency improvement damper. And we want to show you how our damper can help you save money. Just to let you know how we work, our motto has been providing unique value added solutions. So 1996, when I started the company, prior to that, I had worked for about 20 years in a couple of fire heater companies. And most of the companies focused on new heaters, on supplying new heaters. And it appeared to me that maybe there is an opening if we focus on existing heaters. So we made it our mission to improve the performance of existing fire heaters. We have been working directly with owners and end users. Our motto has been do it once, do it right, because that is the cheapest way of executing projects. And because of the time difference between US office and Noida office, we are practically working around the clock. We have been able to execute projects in very, very short time, almost half the time. I can tell you a story about a company in Suriname. They were ordering heaters. I think they needed 10 heaters for a project and they ordered 9. I don't know how it happened, but they looked around everywhere in US and finally somebody said, why don't you contact Furnace Improvements? They came to us. They say, we want to build this whiz breaker furnace, a small whiz breaker heater, and we want it in 6 months. And sure enough, we supplied the heater in 6 months. So that's how fast and nimble we are. Uh, we are always looking for challenging projects. So if you have a heater, if you have a stack damper which is not working, bring it to us and we will fix it for you. So if you have any heater with run length issues, flame impingement issues, high tube metal temperature issues, we love challenges. So challenges us with your project and we will tell you how good our team is. Uh, just to let you know, we work on all types of refinery heaters, crude heaters, vacuum heaters, reformer heaters, coker heaters, CO boilers, waste heat boilers, SCR units, ultra low NOx burners. So we do everything. And this is a list of our clients in the past 28 years. Most of our clients are located in US, but we have worked for HPCL, we have worked for Reliance, not much, but some. We have done some work for Thermex, Indian Oil, KNPC, off and on. We have worked in Europe also, total. So, but Phillips 66 in US has been our largest client for the past 15 years. And we are not just consultants. A lot of people think of us as a consultant actually. And that may be true because we do start with engineering studies. But we are so confident of our recommendations that we offer the services of our engineering group to put those recommendations into practice. And we don't only implement them, we guarantee them that whatever we are recommending you will work. So we are just like any other heater vendor. We have a process group, we have a CFD modeling group, we have a mechanical group, we have a structural engineering, we have a 3D modeling. So we do everything. We do complete turnkey projects. Our first turnkey project was at Citco in Corpus Christi refinery. That was in 2002. And since then, we have done a lot of projects. So we not only recommend or troubleshoot or give you recommendations, we implement them. We also build new heaters. If you don't know, we build new heaters. We have not done maybe about 10 or 15 new heaters in the past few years. And as I said, our approach has been challenging the conventional wisdom, and that's how we have 3 patented technologies. And that is what differentiates us from other heater vendors. We are always trying to provide you with better solutions or software solutions, technology-based solutions. So with that, let us come to the topic of the day. And I'm sure you all know fired heaters, but I still have to talk a little bit about fired heaters. Fired heaters are one of the most important equipment in the refinery. It's a major energy consumer, you know, also major pollutant, actually, major emissions of greenhouse gases, NOx, you know. Uh, Typical fired heaters have 3 components: radiant section, convection section, and stack. And today our focus will be on stack. Uh, in fired heaters, we are burning fuel gas, fuel oil, with combustion air to generate heat, and that heat is transferred to the hydrocarbon, which is flowing in the tubes. 60 to 70% of the heat is transferred in the radiant section, 30 to 40% is transferred in the convection section. And stacks, what we will be talking about today, or dampers, their primary function is safe disposal of flue gases. The secondary function is providing draft in the fired heaters. And that's how we end up with a damper for controlling the draft. I want to make a request that if you have any questions on dampers, please email me at my email. I think I'm more familiar with emails rather than I will try. You can also submit the questions through this go to webinar, but if you are not able to submit it, send me an email and I'll be more than happy to reply at the end of the webinar. So why are we talking about dampers of all the things? Why not something else actually? And as I've told you, I have spent almost 50 years in the industry, 48 in fired heaters. And there have been a lot of practical experiences with involving dampers. So 1970s, I think 77 or I think 78, somewhere around that time, we were commissioning a small furnace in Mumbai at a chemical plant, and there the stack damper malfunctioned. In those days, the damper used to be all manually operated with cable and winch. And I can tell you, those of you who have operated cable and winch, it's really gross. It's very difficult to control. And in those days on cable and winch, you have two markers, one position showing damper is fully open, other position showing damper is fully closed, and you kind of rotate by hand, and it's all guesswork. Uh, in 1980s, I was working at EIL, and I believe the company replaced burners in one of the heaters. And when they started back, they could not start, because somebody had changed the indicator on the stack. We don't know how it got changed, but it was open. It was showing closed. And everybody was looking at outside. Nobody went inside actually. So they had to call an engineer from UK to diagnose the problem. So that's the second experience. 1996, I was working in one of the heaters at a gas plant, local gas plant in Texas, Anderson, Texas. It was a simple hot oil heater, nothing complicated, and somehow we said, okay, let's start tuning it. And it was a challenge actually. In fact, when you operate a manual damper, the furnace started puffing. So it's a challenge. Then in 1998, I was assigned a, a, a training assignment for Landale Chemicals in Houston, Texas. And every Thursday, I would go and train anywhere between 8 to 15 operators for 4 hours. And what these operators told me was very surprising. They said the burner vendor came about 5 years ago. He adjusted the stack damper, and we have not touched the stack damper. So that was very, very surprising feedback. And for all those times, I was thinking there must be something wrong either with the operators, or maybe we can solve some of these problems by putting pneumatic operators. But later on, it turned out the pneumatic operators solved some of the problems, but it still not physically solved all the problems or improved the operation. And then we spent almost 7, 8 years researching on the dampers. You'll be surprised, why do we research? Because we want to get it perfect. If you know about fired heaters operation, there are only two things the operators adjust: stack damper and air registers. There are only two things. So from that point of view, the dampers are important. But from the project manager's point of view, the heater vendor's point of view, the dampers are not important at all. They treat it as a plate on a pipe actually. That's how the dampers are, you know. So in order to make a long story short, I think we may run out of time. So I don't want to keep on going, but we looked at it and we came up with this solution that the existing dampers, most of the existing dampers are not correctly sized. They have lot of design deficiency, and that is why the poor operators cannot control the draft. It is not the operator's fault, it is the damper's fault. The damper is not correctly sized, and that's what is leading to the problem. You can put a pneumatic operator, it will still not work. You can change it from parallel blade to opposed blade, it will improve a little bit, but it will still not go there. So what we find in the real life is most of the stack dampers are kept fully open actually. Nobody adjusts. And as a result, there is a very inefficient operation. Oxygen in the heaters could be running anywhere between 7 to 12%. So that's what has led us to fix this important piece of or important component of fired heater, And that's what we want to talk to you. And especially if you have a natural draft heater, it can help you improve your operation. It can help improve the combustion process. It reduces oxygen and NOx. And it is not only these heaters, you can also do it in other heaters also. I know in Europe, they have tall stacks, 200-meter tall concrete stacks, and they produce tremendous amount of draft in the heaters. If you have a 600-foot tall stack, you can imagine how much draft it will produce. And we did an exercise several years ago. I think we even have an example in this presentation. So a lot of improvement can be done by simply fixing your damper, by making it correct. By sizing it correctly, you can get a lot of savings, and we are there to help you. Before I forget, I want to thank my team at Furnace Improvements, the process team, the mechanical team, the SolidWorks team for preparing this beautiful presentation for webinar today. It's their hard work which has me going in this presentation. They have done all the presentation. So thanks to Furnace Improvements team, you did an excellent job. You know, I'm a very demanding person. I'm a perfectionist. So I keep on sending them back things which I don't like, and we keep on recycling it till it is perfect for me. So if you have a heater or a damper, send us for a free evaluation and we will help you save money. So this thing I already covered actually. The operators only have two things or two components in fired heaters in the field: burner registers and stack dampers. And sadly, both are in the bad shape. Burner registers also, we can talk it on some other day, how we can fix the burner registers. But today we will tackle the stack dampers. So I did some research. It turned out in the earliest heaters, there was no damper in the stack because most of the burners were premix burners and they were draft independent. They were not dependent on draft. So nobody used to provide dampers in the stack. So problem solved. 1960s manually operated dampers with cable and winch got installed in the stack. In 1990s, industry started adding pneumatic actuators. There are still a lot of dampers which don't have pneumatic actuators, but there is another reason why people are adding pneumatic actuators. The number of operators in the field have been cut down. So when you cut down the operators, you have to use pneumatic actuators and operate them from the control room. So that's another reason why industry started adding pneumatic actuators. In 2000s or whenever they added, maybe a lot of people changed from parallel blade to opposed blade. It did improve the performance a little bit. So we do heater studies, troubleshooting, revamping for a living. And as a part of that, client sends us operating data, typically anywhere between 3 to 5 years, and we analyze the heater operating data to find out what is wrong in the heaters. So my team studied 25 heaters. I told them, look at all the past projects and tell me how the XSO2 value is. And here, these are the real values. And you can see it's ranging anywhere between 7% to 13%. The 13% heater, you can ignore it actually. It's a very small heater in India, and we are fixing it right now, We are fixing it. We have told we will improve your efficiency. But delayed cooker heaters running at 7.6, boiler running at 8.6. Boiler is normally forced draft. So you can see uh, things are not correct. And one reason could be the low fuel gas pricing, the low fuel gas pricing. So look at how much savings we can help you. This is a heater, inter-reactor heater, running at about 11.5% oxygen. And if we go to 3% oxygen, we can go all the way about 17%, 16% improvement in the efficiency. It will save us almost $750,000. And if you add the greenhouse gas reduction credit now, I think a lot of governments have started adding carbon tax or greenhouse gas reduction, and assume about $80 a ton, that will almost make it like $1.5 million. So the damper will get paid out in about 2 months. I'm taking two, even if I take $250,000 for installing the damper, which is still on the high side, but let's even take it. So within 2 months, the damper will pay out. So that is how fast the efficiency improvement potential. This is another one. This is the one in India actually we are talking about. And in India, the only thing difference is that the fuel gas price is very high. Instead of $2, which is in US, in India, the gas prices or the energy prices are $12 per million BTU. So you save almost $250,000 just on fuel savings alone. And the cost of that damper may not be more than 50,000. That's I think 3-foot damper. So we are looking at again a 2 months to 3 months payout period. So most of the dampers will pay out in less than a year. Most of the companies sometimes want a payback period of less than a year, and I'm very sure that it will pay back in 2 months to 3 months. So let us think about how we reached here. How did this thing happen actually? And fire heaters are built for a long time, 30, 40 years. Feedstocks, operating conditions keep on changing. Process licensors, designers typically provide 10 to 20% margin in fire heater duty. It's a good practice, nothing wrong with it. And then APA 560, which is a Bible for designing fire heaters, constructing fire heaters, says provide another 120% margin on over design of stack. So we provide another 120% margin. And then stack needs to be designed for the maximum air temperature of anywhere between 95 to 105, summer design, which may be there for 2 months, you know. So all these things keep on adding margins. And I have not told you the biggest margin we provide these days. And the biggest margin is environmental considerations. In the past 30 to 40 years, environmental considerations have come into play. Ground level concentration of pollutants have come into play. And as a result, the pollution control boards, EPA, they specify minimum height of the stack. A lot of places they will specify 100 feet. A lot of places they will specify 200 feet. I believe in India it is about 200 feet for new heaters. In US, it is, I think, still about 100 feet. You know, so once you start going with the minimum stack height, the stack design becomes important actually. And most of these stacks are self-supported, so they have to be structurally stable. In order to make them structurally stable, we have to follow h by d. Height h means stack height and d means stack diameter. Should be around 15, 14, 16, So as a result, we end up with a larger stack diameter. So these are the three types of stacks we normally build: straight stacks, conical stacks, or telescopic stacks. And we'll come to them. But generally, this is because of the environmental reasons, we had to put a minimum stack height. So let's take a case, typical case, when you're process engineer, you are sizing stacks, you go with a stack velocity of 25 to 30 feet per second, you design the stack, calculate the stack height based on the draft losses. Let's say I come up with a stack design of 3 feet diameter for a small heater, maybe 15 million BTUs, 100 foot tall. Now, I make the data sheet. The data sheet goes to the mechanical group. They go to the structural group. Structural engineer says, for a 100-foot stack, I need a 6-foot diameter. So immediately the diameter goes from 3 feet to 6 feet. Now to satisfy process conditions, process engineers or emissions, EPAs, we provide a stack tip on the top of the stack to get the specified velocity. Some people say 40 feet, some people say 50 feet, whatever velocity you want, we give the stack tip. And that is how we satisfy the emissions. So now look at what has happened. The diameter went from 3 feet to 6 feet, which was 2 times. Area became 4 times. Velocity went down by 1/4 time. And when the velocity goes down by 1/4, the pressure drop goes down by 1/16 actually. That's how low the pressure drop goes. Friction delta P goes down even lower actually. So what is happening is everything changes. And when everything changes, things get built up, and then later on they find that they have a stack diameter or a damper which is 2 times the size of the damper. If you are a process engineer, if you are an instrumentation engineer, if you have bought control valves, you will know that typically the control valve that we provide in lines is one size lower than the line itself. If we have a 6-inch line, we normally go with a 4-inch control valve. And here, what we have done is instead of one size lower, we have gone 2 sizes twice, 2 times higher actually. So I will try to explain you the problem in very simple terms. This is the real problem. And what we are getting into is high air leakage and high excess O2 in fired heaters. So you end up losing energy, you end up having more CO2, you end up having higher emissions, everything goes bad. You can have a lot of tramp air, you know, and when you have tramp air, you don't know where this air is coming from. Is it coming from burners or is it coming from the header boxes or other openings? It can also lead to after burning. So a lot of things can happen, bad things can happen when you have high draft. So just to give you a little information on conventional dampers, generally they are single blade or multiple blade with manual or automatic actuations. They are both moving in the same direction or opposite direction, but they are both moving simultaneously. And I have shown here two. We have shown the parallel blade linkage and parallel blade operation. And this is the opposed blade, which is in the opposite. So when the stacks are oversized, the moment you open a little bit, uh, you start getting immediately flow. So you open 10% or 20%, you get 80% flow. And the control goes haywire. And we blame the poor operators. The operators say they can't do anything. So they just leave the stack damper open. We are still not talking about another problem with the stack dampers. But this is what happens, 20% opening, and it becomes insensitive, insensitive actually, or very sensitive. So what we are doing is very simple. We are custom designing your damper. We take your damper, we take your heater, we check the operating data, we find out just like you do control valve sizing, we do the stack damper sizing. And what we have done is, in order to give you full flexibility, we have come up with a design with two actuators. We could have done it with one actuator also, but in order to give you the full flexibility, we came up with a design of two actuators. So when you are controlling, one set of blades is kept fully closed and the other set of blades keeps on operating. And if you want to open the stack damper fully, you can always do that. It's not that you cannot do it. You can always open the full capacity. Suppose you want to fire 200 million BTUs in a 100 million BTU heater, you can always do that. So that's where we are. So it's a precise control and it's custom designed for your heater. It's not like one set size of damper works for all the heaters. So another thing what we found is in most of the dampers, there is a gap provided around the blades so that it does not stick to the refractory. It does not foul with the refractory. So we typically provide an inch or 2-inch gap all around the blades, all around the circumference of the stack. And what we find is there is a plenty of leakage taking place when you have this type of clearances, And this leakage can be anywhere between 15 to 30%. So even when your damper is fully closed, you're leaking about 15 to 30% of flue gases. So with that, the control becomes even more difficult. And what we have done is we have tried providing seal plates so that when the damper is closed, you don't have any leakage, And what it does is it gives us a much better control on the stack damper. So simple things like putting a seal plate improves the control dramatically, This is I went to Europe in Germany, I believe, to tune some heaters, 2009. And you can see the draft at arch was almost 6 times, 15 millimeter, 0.6 inches water column. It should be. And I closed the stack damper and brought it down to about 0.3, little bit, 0.25 or so. And you can see the O2 level came down drastically, I mean, they were surprised how the fuel gas consumption came down from here to here, So the proof is there. It is not something hypothetical that once you control the draft, your excess O2 will come down, your performance will improve substantially. And this is the chart my team has done, you know. So this is, I told them this is the 3% O2, then we have 6%, 9%, 12%, and 15% O2. And this is the y-axis is efficiency, this x-axis is flue gas temperature. And you can see how much savings can be done, you know, over here. Amazing amount of savings can be achieved by controlling the stack damper properly, controlling the draft. And this is what we are showing you, the leakage area, the area in the pink, which I told you about 1 inch or 2 inch gap, you know. And this is my team has done that for a 3-foot damper, the leakage area is almost like 30%, and it keeps on reducing, you know. It also depends on the number of blades. Like if we have more blades, we will have more leakage. If we have 4 blades, we will have another 3 paths in the center. So this is what is having a problem on the control, you know. It's like having a bypass open all the time on a control valve, you know. That's what it amounts to. Like you have a 30% bypass, you put on a control valve, which is already working, and then you try to control, you know. So it won't work very well. So we find that it needs to control. So I have a case study here. This is in Europe, actually. We just supplied this damper about 6 months ago. So this was a crude heater, natural draft crude heater, 70 million BTUs, and twin cell radiant box. Design excess air was 15% or 3% O2. It had a 7-foot diameter, 6.5-foot diameter, 88-foot length stack, you know. Existing damper, manually operated, you know. So they came to us, they were having problems actually. So we said, okay, we estimated about 7%, 6 to 7% O2 in the furnace based on the data. And we realized that the stack velocity is very low. So the damper was oversized. So pressure drop was again very low. The arch draft was very high. You can see 0.45. Instead of 0.1, the draft was around 0.45. You know, there was a leakage taking place. The heater efficiency was almost 79%. So we ended up reducing the excess air from 33 to 15 and redesigning the damper and increasing the damper loss, you know, from 0.08 to 0.46. And we did that by what we just told you, you know. We created 2 blades. We said, okay, if it's a 2-blade damper, we will leave it 2 blades. And they did want a 3% leakage all the time. So we did put seals and put a gap here so that they can have 3%, you know, leakage even in the fully closed position. And that is how, you know, we redesigned the damper. So 2 blades are closed and 2 blades are open. So we are getting almost 50% area. And then we can still close these 2 blades, you know, if required for lower area. Because what we found is you only needed a 4-foot damper, 4.5, 4.3 inch damper is what you need actually. So very, very simple. I mean, all it is calculating a CV of a control valve of a butterfly damper, you know, and we improved the efficiency by almost like 3%. I think it is more actually, but we have not the correct data, but around 3% efficiency improvement, you know. I think it paid out in about 6 months. So this was a damper which was rebuilt in place. You don't have to change the damper. You don't have to remove the stack. We supplied these components, and when they had a turnaround, they just retrofitted the new components and put new actuators, and the whole thing was working, you know. And the client has been very happy, you know. So that's another case of a coker heater. We studied, it's in Texas actually. Very large coker heater, natural draft, you know. We did the retubing of this heater, the radiant section, complete radiant section retubing of this heater. And when we looked at it, the O2 was running almost like 7%. One cell was 7%, one was 6.6. So we looked at the issues and we found the damper was very oversized actually. And there was no way you could control the existing damper. So we came up with a new design with dual actuators. It has not been implemented actually. Uh, had they ran out of time and they said they will do it at the next turnaround, you know. So I can let me see if anybody has any questions. If anybody has any questions, I can answer them. No questions yet. Okay, let me see on my email if I have any questions. All right, we will continue going. So this is another project where we did the damper analysis. This was running at about 7% oxygen, and stack height was much higher. Existing damper single blade could not control the draft at the arch. So again, we gave them a new design. I'm not sure the efficiency went up by 6%. I don't recall whether this has been implemented or we have made a recommendation, you know. So you can see this is the draft profile, this is the existing, and this is the proposed, you know. So we make a big, you know. So we are so convinced of this technology that if we are supplying new heaters, we are putting a efficiency improvement damper as a standard equipment, you know. So this is a crude heater we have supplied. It is still not commissioned. Actually, it was supposed to be commissioned this year. It will be commissioned next year. But this is a crude heater where we have supplied a new damper actually for them. This is 8-foot diameter, 4-blade pneumatic type, 91 million BTU. So we, on our own, we have supplied this efficiency improvement damper so that they can have uh, efficiency savings, you know. And you can see over here, actually, if you look at the flue gas velocity is 15.7. So the stack diameter is 8.5. Length is 72. So if you look at the L by D, it is not even 10 actually. That's how broad this stack is or wide the stack is. So we did the sizing, we realized that we needed a lot more pressure drop in the stack, in the damper, to get the proper control. And there is something which is known as damper authority. Just like when we do control valve sizing, we talk about 30% pressure drop of the downstream being in the taken in the control valve. So 30% of the total pressure drop is taken in the control valve. Similarly, damper authority also has something similar. So you assume 30% pressure drop, and then you come back with the required size or required velocity. So the principles are the same, and you can see the arch pressure drop, damper pressure drop over here. So we calculate the net free area of 22 square feet, which is total area is 56, which is 2.5 times more than what we need actually. So anyway, once we provide the dual actuators, you can always go to full area if needed, as I said, and we can easily get 22 area by keeping the two blades closed and then by adjusting the rest of the two blades. So it's a lot easier. This is 56, and if we keep two blades closed, it is 28, and then we can adjust the inner dampers to get the 22 area if needed. So this is what the efficiency improvement damper looks like. It is basically the same damper. This is, although it's a lot more reliable, we try to make sure that the damper is very reliable and does not fail, or provide all the required specifications, indications, actuators, hand wheels, all those type of things. And you can see this is the, if you don't have if you have a conventional damper, then you will automatically have 15% leakage even without this opening. So this is how this will be opening, and this is how the efficiency improvement damper will be working. So it's a much better, I should say it is a safer operation. Because if you have a conventional damper, you will again have the same problems, and ultimately the operators give up, and then they say, okay, it's it doesn't work, so let's just leave it fully open. So we don't want you to be leaving your stack dampers fully open and wasting energy, having high emissions. We want you to be, and you can see we have done this comparison uh, with the pressure drop across the coil, come up with the velocity. This velocity is 14 feet per second. We are going about 27 feet per second, almost double. And by doing this, we can increase the pressure drop from 0.01 to 0.04. If you look at the damper authority, we have improved from 5 to 13. We can do it even higher if required, but that's what we are kind of thinking. So stack dampers, they are never sized or customized, as you know. In this industry practices, stack diameters is much larger due to structural stability reasons or stack design reasons. Our efficiency improvement design customizes and provides a flexibility, or improves the damper control characteristics. And it's done for your specific heater based on your past operating data. And as a result, you get accurate control of excess oxygen and draft in fired heaters. We can convert your existing damper into efficiency improvement damper. And this will improve the safety, reliability, and efficiency of fired heaters. So thank you again for giving me a patient listening. I really appreciate your time. Again, I want to thank my team at Furnace Improvements in Delhi to prepare this excellent presentation. So I do have a question. It says, what precautions are to be considered due to presence of a partition plate in an off-take configuration from pressure drop point of view? So Mr. Jayapal, I don't, the partition plate should not make any presence of a partition plate in an off-take configuration from pressure drop point of view. I don't think you will need any precautions because the partition plate is basically for reducing the pressure drop. That's typically why we provide a partition plate in off-take. And the damper is going to be downstream. So we can go with the same design. We don't see any issues, with the partition plate. Well, thanks for the question. And if anybody else has any question, he or she is more than welcome to. We have a couple of minutes left. And this is a very simple concept. All we are doing is customizing your stack damper to meet your fired heater. That's all we are doing. And we can do it very effectively and it can save you money. That's what we do for living. Analyzing heaters. So we will analyze your operating data. We will run the simulations, check how much draft is available, how much draft needs to be used across the stack damper. And then we will customize and give you recommendations. So once again, thank you all for listening and hopefully I'm sure you would have learned something new and well worth your time. So thank you again. And we look forward to the next webinar. We will put this webinar on YouTube and even on the GoToWebinar site. So hopefully you will enjoy it even more. Thank you. Thank you and have a good day. Blessed day.